heat? Easy. Ask any fuel oil customer. Simply set the thermostat to heat and pick your comfort level, then relax. Oil heating is that easy for your customer. But for you, it's a different story. That's why we've prepared this video training library, to make it easy for you to understand oil heating equipment and so you can effectively serve your customers. Now watch and listen as we explain the fundamentals of fuel oil heating. Fuel oil, the energy source that helped pioneer automatic heating, is just one of the final petroleum products we have come to depend on. Others are petroleum, ether, gasoline, naphtha, benzene, and paraffin. But exactly what is fuel oil? Oil deposits beneath the ground and the oceans of the world are the source for crude oil, which is then transported to refineries. There, the many oil products are drawn out of the crude through distillation and other processes. Then the oil is shipped to oil dealers for sale to the consumers. Fuel oil is a valuable heating source because it is a hydrocarbon. Taking that name apart, you see that the fuel oil hydrocarbon is 15% hydrogen and 85% carbon. Both hydrogen and carbon are flammable when combined with oxygen in a chemical reaction called oxidation, or burning. Fuel oil is just one of the many hydrocarbons that can be burned or oxidized. Other hydrocarbons are natural gas, propane, coal, alcohol, and an ordinary candle. Hydrogen, carbon, and oxygen need to be ignited with sufficient heat in order for oxidation to begin. This ignition can come from a spark or from another flame. Once combustion begins, the process can feed on itself to continue. In the case of the candle, the heat of the match alone vaporizes the wax on the wick. The burning wax generates heat, which causes more wax to melt, vaporize, and feed the wick, enabling it to continue to burn. To stop, you must either run out of fuel, in this case the wax, or oxygen. But what about fuel oil? How does it burn? And what must you know about fuel oil to install, adjust, and service a fuel oil burner successfully? First of all, fuel oil for heating comes in several grades. In the number 1 oil types, there are kerosene, K1, and JP5. JP5 is a type of jet fuel that is sometimes used as fuel oil. Number 2 fuel oil is usually supplied in one grade. It's also the diesel used in powerboats, trucks, and automobiles. Both 1 and 2 are made during distillation at an oil refinery, and each has slightly different characteristics which make big differences in the way they produce heat. First is energy content, measured in British thermal units, or BTUs. A BTU is the amount of energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. BTUs are important when you calculate heat loss and burner firing capacity. In number 1 fuel oil, there are approximately 135,000 BTUs per gallon. In number 2 fuel oil, there are about 140,000 BTUs per gallon. Second is flash point, or the temperature at which vapors are produced to allow a momentary flash of flame. Both number 1 and number 2 fuel oils have a 100 degree Fahrenheit minimum flash point. When storing oil in hot weather or hot locations, remember that the flash point becomes an important safety consideration. Viscosity is the measure of oil's resistance to flow. It tells how long it takes a particular grade of oil to pass through a specific opening size at a specific temperature. The viscosity rating shown here means that it took 35 seconds for a specific amount of fuel to pass through a standard measuring orifice at 100 degrees Fahrenheit. The higher the viscosity rating, the slower the oil will flow through the fuel supply system to the burner. The lower the rating, the faster the oil will flow to the burner. Viscosity becomes a prime consideration when the temperature gets low. When the temperature drops down into the freezing range and lower, a point is reached where oil will not flow at all. This, of course, can cause serious problems in a fuel oil heating system. This frozen beaker of oil will give you a good idea of what can happen to the oil in outdoor storage tanks and supply lines in freezing weather. Pour point is 5 degrees Fahrenheit above the temperature at which a particular fuel oil will barely flow. However, you can change the pour point in the field by mixing in a lighter oil, such as kerosene, or by adding a chemical agent to act as a pour point depressant. Cold weather also causes wax crystals to form in the oil. These crystals can clog filters and strainers and stop the oil from flowing from the tank and supply lines into the burner. This temperature is called cloud point. It is usually 20 to 30 degrees Fahrenheit warmer than the pour point of the oil. Now, let's see how these characteristics affect the ways heating oils are used. Number 1 fuel oil has a lower distillation temperature, flash point, viscosity, pour point, and cloud point temperature than number 2 fuel oil. For cold conditions, an oil refinery or dealer can blend in at least 25% of number 1 fuel oil to lower the pour point. Let's take another look at the combustion process to understand the air to fuel ratio. Remember the candle? The same chemical results take place when fuel oil is burned. The oxygen in the oxidation process comes from the air, but air is only 21% oxygen. The rest is primarily nitrogen, which doesn't take part in combustion, but passes through the process unchanged. Now let's see what happens when the fuel oil burns. Fuel oil is 15% hydrogen and 85% carbon. Unlike nitrogen, both hydrogen and carbon combine with oxygen during combustion and form new chemical gases. Later, you'll see how to measure these new gases in the flue to guide your adjustment of the combustion process for optimum heat and efficiency. But for now, let's look at the combustion reaction, starting with carbon by itself. Carbon combines with oxygen from the air to become carbon dioxide, a new gas, and heat, which we will call heat number 1. Nitrogen is also present, but unaffected by the process. Fuel oil also produces heat from the hydrogen it burns. Hydrogen combines with oxygen from the air to become water in the form of steam or vapor, and heat, which we will call heat number 2, to differentiate it from the heat number 1. If you compare the two equations, you'll notice an important difference in the combustion results. The carbon produces carbon dioxide, CO2, and the hydrogen produces water, or H2O. But unlike this theoretical result, the actual combustion process in a burner uses excess air, also called reserve air. Excess air is readily available and provides sufficient oxygen to make sure that the fuel oil is completely burned. After the burning, there's excess air left over. Oxygen that is not consumed during combustion stays in the excess air that passes up the flue along with the carbon dioxide. These instruments read the outputs of fuel oil combustion and guide you in adjusting the burner based on the excess oxygen or the carbon dioxide, along with smoke and heat. You'll see how to use them in Volume 5. Watch what happens when we try to burn liquid fuel oil. It extinguishes the flame. This makes it safe to handle and transport. But why doesn't it burn as a liquid? For the same reason this log doesn't burn when exposed to a match. The mass of the log is too great for the heat source to raise its temperature to ignition point. Instead, it simply dissipates the heat. But shave the log into pieces too small to dissipate the heat, and you quickly have a fire. It's the same with fuel oil. You must first have a small amount with sufficient oxygen to ignite it easily. But how can you get the fuel oil into this state? Vaporizing is one method. Atomizing is another. This kerosene lamp is an example of vaporizing. As the lamp burns, the wick pulls the oil up from its dense liquid state in the base, exposing it to oxygen and heat, producing continuous combustion. The combustion is controlled by regulating the length of the wick. But combustion by vaporizing can cause excessive soot unless the fuel is completely burned. Number 1 fuel oil is the preferred fuel for a vaporizing oil burner. It vaporizes and burns easier than number 2 and creates less soot. Today's high-efficiency burners atomize number 2 fuel oil for efficient combustion. The oil is placed under pressure and forced through a finely machined nozzle to produce a controlled, mist-like spray of minute oil droplets. In this atomized state, the oil droplets are easily ignited with just a spark. Here, the spark is applied in an actual burner head using high pressure and an atomizing nozzle. A chain reaction occurs as droplets burn, then release their heat to ignite other droplets. This ends Volume 1. This video training library is provided as a service to the oil heat industry, brought to you by R.W. Beckett.